Hello, this is the next video in a playlist that I'm calling Hypothesis Testing, and we're doing a little mini-series within that playlist. And this is part 5 of a little series on two-sided, uniformly most powerful tests in the one-parameter exponential family. And I'm going to pass you off to part 1 where we talk about the theorem that, it creates these uniformly most powerful tests. And it's pretty fascinating. The theorem is one of many extensions of the name and Pearson lemma that allows these to be uniformly most powerful. So here we're going to look at we're going to be in the binomial setting. So x takes on the value 0 or 1. So it's a Bernoulli with parameters 1 and p. P is the probability of observing a 1. We take a sample of size n. P is in the parameter space omega and can be anywhere between 0 and 1. So the distribution function for this, or probably mass function, is commonly written like this. X takes on the value 0 or 1. We can rewrite this, take the 1 by itself and then the x, but then we take it below, and it can be rewritten like this. And we do this because then it's easier to see that it does fit in the exponential family. So this is a function of the x's. This is a function of the parameters, and this we take the log and then exponentiate it so it doesn't change, and we get this. And this is what we call q, and it is a strictly increasing function in the parameter p. Our test statistic ends up being the sum of this x right here, so it's the sum of the x's. And then the test that we want to test, the two-sided test, the null hypothesis, is p less than p1 or is p greater than p2. And the alternative is it in between those. And this is for an alpha level test. And the theorem in part 1, which is an extension of the name and Pearson lemma, it tells us the uniformly most powerful test is this. So our test function phi takes on the value of 1 if our test statistic is between two values, C1 and C2. It takes on the value gamma 1, which means we reject the null hypothesis with probability gamma 1 if our test statistic is equal to C1. It equals phi equals gamma 2 if our test statistic is equal to C2. And at 0, it says do not reject the null hypothesis if our test statistic is less than C1 or greater than C2. Now, to find the values of C1 and C2, there's what's called two-side conditions. Now, the name of Pearson lemma has one side condition. This extension has two. And it's really the expected value of our test function under P1 and then P2. So I just say PI to capture both of those scenarios. And those both equal to alpha. And then we can solve a unique value for C1, C2, gamma 1, and gamma 2. Now, when we take the expected value of our discrete variable, the discrete function phi, it takes on the value and then the probability of observing that value. So this is 0. And then here it takes on gamma 2 times the probability of observing that, gamma 1 times the probability of observing gamma 1, and then 1 times this probability, which is here. And so this creates two equations that equal alpha. Now, this creates unique values for C1, C2, gamma 1, and gamma 2. And so technically I probably should say it creates essentially unique C1, C2, gamma 1, and gamma 2. Now, for the binomial setting, it is unique, but there are some crazy examples where it's not quite unique, but when it's not unique, the other cases have probability 0, so you never see them. So they're essentially unique, but in this example, it is unique. Now, solving for C1 and C2 and gamma 1, gamma 2 is actually pretty tough by hand to find an equation. But in R, it's fast. You just cycle through all possible C1 and C2 values, solve this equation, and see if it equals alpha. It does, you're done. If it doesn't, then you're not. And you can solve for these in a matter of, a split second. So on the next page is the approach that I use in R to solve this. Now here, so we're going to assume that we know C1 and C2. It's fixed. Now granted, we're going through all possible combinations. So we assume C1 and C2 is fixed, and we know, of course, the test statistic. Then this becomes a constant. So let's call this value probability 1, or P1, which now I'm reflecting is probably not the best thing, because P1 and P2 we used for these cutoff values, possible values for our the probability of a success. So I probably should have called it X1 or something, but this is P1. This is a constant. Let's call it P2, P3, and then the next equation, this is P4, P5, P6. So what I just said was we take those two equations on the previous page, and we create these cases right here. So we're going to solve for gamma 1 and gamma 2, assuming that we know C1 and C2. Now here, if we take equation 1, we can solve for gamma 1, and we do that. Then we take this and plug it in 2, and then solve for gamma 2, and we get this. Then we take this gamma 2 and put it in here, and then we solve for gamma 1. And that's what we do. So these are the two values, gamma 1 and gamma 2, that forces those equations to equal 0.05. Now the crazy thing is, for every C1 and C2, we've just created equations that are always equal to alpha. But one thing you have to consider is that these are part of the test function, and the test function can only take on values between 0 and 1. So if we get crazy values that are outside of the interval 0 to 1, we know that they can't be a part of our test function, which tells us that those C1 and C2 values that generated these can't be our critical region, can't be the cutoff. Okay, so that's essentially what we do. So what I just said in step 4 is the test function phi is between 0 and 1. So we remove any gammas that are outside 0 and 1. It's sort of hard to find the C1 and C2 by hand. Not impossible, but as I was going down this route, I'm like, why do that? It's so easy to solve in R. So I stopped, and in the next video we'll look at that. So we check all combinations of C1 and C2. We see if they meet this criteria. If they don't, we get rid of it. If they do, we keep it, and it's unique. So there's only one set of C1 and C2 that makes this possible. So our next video will illustrate this in R. Well, that's all I have for this video. Hopefully you enjoyed that. I sure did. Please like the video and subscribe so you don't miss the next one. Thanks. Bye.